Okay, we are going to talk about the free body diagrams that we looked at last class and how to turn those into equations, just like we did with regular free body diagrams in Unit 2, to solve questions. Okay, so this is all stuff we've kind of already talked about, so this part should go pretty quickly. In order for an object, like a meter stick or a board, to balance, both the torque and the forces have to be in equilibrium. And we know that. We've already talked about that multiple times. So this object is not rotating, and therefore it is in a rotational equilibrium, so the torques have to be equal. But it's also not accelerating upwards or downwards, and therefore it's in a force equilibrium. Okay? So again, things we've already done. You've already been able to answer questions like something like this with our meter stick lab. The magnitude of the sum of the torques from the yellow pieces has to equal the torque from the red piece, right? So this one, the red piece, it's forced down at its distance away. Okay, biggest thing to remember with torques is that you have to include the distances. Has to equal the torque from each of these. So its force times its distance plus the next one's force times its distance plus the next one's force times its distance. Okay, why do I have them as this equals that? Because in reality what it is that all of them added together should equal 0. One of these sides would be a negative torque, right? So we would consider the yellow ones to all be negative. So red minus yellow 1 minus yellow 2 minus yellow 3 has to equal 0. It's just normally quicker to write it this way, that one side equals the other. Just it minimizes one step of writing. But if this were an AP test, you would want to say somewhere that what you were doing was creating a torque equilibrium, a rotational equilibrium. Okay, so same thing. Counterclockwise torque, clockwise torque, they have to balance out. Okay, and then the sum of the forces also have to balance out. Okay, this pivot here in the bottom has to be holding up the weight of all of these things. So the normal force pushing back up on this beam has to be equal to the weight of everything that's on it. And so we get this picture here. Okay, you've got the downward force of the red, you've got the downward force of the board, the downward force of each of those pieces. That has to be completely balanced out by the pivot. Okay, so we are going to use torque on a lot of different situations. I mean, we used it on a meter stick that wasn't turning, right? So we know that we can use torque when it's not turning. We can also use it on things like a ladder that's leaning up against a wall, or a beam that's attached to the wall here with a string. Even this cat here on this piece of wood. If the cat takes one more step, this thing can rotate, right? It will rotate around this sawhorse. This, if we cut the string, could rotate. The ladder could rotate around the bottom there if I decided to come along and push it backwards. So we have lots of different things that we can use that can be considered rotational, even if they're not technically rotating. Okay, so this is all just in words what I just said. Okay. All of those objects are in translational equilibrium. They're not accelerating in a straight line in any direction. Okay, they're also in rotational equilibrium. They're not accelerating rotationally. They're not turning, spinning, getting faster in any way. But they could. Okay, and so therefore we can use F equals ma, okay, Newton's second law, the fact that the total force has to equal 0. The net force has to equal 0 for them not to accelerate translationally. And the net torque, because remember, force and torque are just the translational and rotational equivalent of each other. So the net torque will also have to equal 0. Okay? And what we're going to do is we're going to look at questions like this. And there is no way to solve this question with just forces. And so we are going to use torque and force together to solve the question. Okay, you should have the question on your piece of paper, so I don't have to read the whole thing to you. But you've got a beam. The beam has a mass, which means you're going to have to account for that in your free body diagram. The person has a mass. And both of these supports are pushing up, holding up the beam and the person. Okay, so you've got 4 different forces here doing things. And what we want to know, if this is all sitting still in equilibrium, what's the magnitude and direction of the force from the far left support? Okay, the way that we're going to do this is to use torque. Why? Because I can't use forces. I have 2 unknown forces pushing up. That means I can't figure out what each of them individually is going to be using, because all I know is the total. I know that the total force up has to equal the weight of the beam and the person, but I don't know how much each of those gets. So the way that we're going to do this is we're going to use torque. Okay, here is the picture drawn as a free body diagram, sort of. I should have put arrows up for each one of these supports, but we do have the downward forces here. Okay, we know the length of the board, so the center of mass of the beam is right here, which is at 1.5 meters from this support and 0.95 meters from this support. Okay, and then we know that the person is 0.1 meters away from this right-hand beam. You get to choose a pivot point that makes your math easier. I'm going to choose the left beam. Why? Because I want to show you that it actually doesn't matter which side you use. So I'm going to choose one that some people might go, oh, well, that's the wrong one. You should have chosen the right beam. It doesn't matter. Okay, you can make whatever you want on this beam your pivot, as long as it helps you do the math. I could have chosen way over here on the left. It wouldn't have helped me. I could have chosen this one. I could have chosen the center of mass of the beam. I could have chosen this support. I could have chosen the person. Okay, now I'm going to tell you, choosing anything other than the left or right beams is kind of silly, because the whole reason for doing a torque equilibrium here is to be able to get rid of one of the unknown forces. Okay, so by choosing the far left beam, it's now at a distance of 0 from itself, right? So it doesn't get included in the torque equation, because torque is force times distance. Okay, so if I write out that my total torque is going to equal 0, my total torque is the beam, the right support, and the person, those 3 torques. Well, the beam is going to be pointing down, give us our negative direction. The support, okay, we don't really know, but we know it's pointing up, so we're just going to leave that as a positive. But if it came out negative somehow, that would mean it was pushing down. And then the person is pushing down, and we have their weights and their distances that they are from the pivot. If this is what we called the pivot, this is the distance that that force is being acted on away from the pivot. So with this right hand support, it has to be the whole 2.5 meters, because it's how far is it away from the support, from the other support. And then the person, it's 2.6 meters, because it's how far away are they from what we called the pivot. And then I can go through and calculate for the right support. Okay. But Mrs. Kosh, the question said the left support. Okay, that's fine. Now I have a number for the right support. I have 3 of my 4 forces. I can look at a force equilibrium. The total force has to equal 0. So the force up from the left support, the force up from the right support, and then the force down from the board and the person all have to add up to 0. So the force left plus the other upward force, which is what we found here, minus the downward force of the beam and the person, gives me that the left hand support is 8 newtons. It's pushing up with 8 newtons. Okay, so did I do it a little bit longer than a way that was a little bit longer than I should have? Sure, but that's why it doesn't. It's okay. You get to choose the pivot as long as the math works out. Sometimes will it take you a little bit longer if you choose, the wrong one? It's not wrong. It just takes you longer. But yeah, you'll get there. Just what you're trying to do when you choose your pivot point is choose something that gets rid of a force at least, or 2. It leaves you with only one unknown. Okay? So if you look at this, this should kind of make sense. The right hand support over here is holding up the majority of the weight. It's holding up most of the person in the beam because both of them are very close to it. Whereas this left hand support is really holding up very little. And the second question asks, well, what happens, or how far can this person move before the whole thing just tips over? Okay, and if you look, with this left hand support only holding 8 newtons, she's not going to be able to move very far. Okay, because when this tips over, this support doesn't touch the beam anymore, which means that's going to be a force of 0. So what we're going to do now is just create a situation where the left support doesn't exist anymore. It doesn't push up, and let's balance this whole thing right on the right hand beam. That's how far she can go, okay, to the point at which it's all balanced on the right hand beam. So the total torque is still going to equal 0, but now it's the beam and the person, and I've chosen this point as my pivot point instead. So the only two forces I have now are the beam coming down on this side and the person coming down on this side. Okay, so the beam is not going to change. It's always in the center of mass. So that beam's weight is 103 newtons, and it's 0.95 meters away from what I've now called my new pivot point. The person, 774 newtons, and we want to know how far she can go. She was at 0.1 meter. She's got to go a little bit more, so x plus 1 meter. And now I can solve that for the x. She can move another 0.026 meters. She can move 2.6 centimeters before she tips over. So she's really right there. Okay, she can just scooch up just a little bit and the whole thing tips. All right. The other question that we have on this piece of paper is this one with the shop sign. Okay, and what we have is now an angle. And yes, we can do things with angles. We just have to remember that we have to keep things perpendicular and parallel. So the beam, okay, is the item that we're really looking at. All of the other forces are acting on the beam. So we're going to draw an extended free body diagram for the beam. And we have tension. That tension is going to be in an angle, which means we're going to have to solve it for its vertical portion and its horizontal portion, because the vertical portion can create torque. The vertical portion at 90 degrees is what is going to allow you to rotate this beam. The horizontal portion doesn't create any torque because it's horizontal to the beam. It won't make it spin or rotate. It's actually just shoving the beam into the wall. Okay? So we want to find the tension in the wire and then the horizontal and vertical forces exerted by the hinge on the beam. So we're going to draw our free body diagram. And if we look at our free body diagram, we've got a lot of unknowns now. Okay, we've got the weight of the beam and the weight of the sign, but then our vertical, our horizontal, and our tension are all unknowns. So when we go to start looking at a torque equation, let's find a place where we can get rid of as many unknowns as we can, which would be over here. If I put my pivot right here at the hinge, V and H disappear because their distances are 0. So now I can say that the torque from the beam, the torque from the sign, and the torque from the vertical portion of my tension are the only three things that are going to be involved in my torque equation. My net torque is equal to 0. I've got the 135 newtons down, and you have to look at the numbers and do the math. Remember, the beam's center of mass has to be right in the center of the beam, so I had to figure out that it was halfway from this end to this end, and that was 1.7 meters. So the distance to the actual mass of the beam is 0.85 meters. And then I have the sign at the full length of 1.7 meters, and I have the vertical portion of the tension, and in the question it said it was at 1.35 meters. So go ahead and solve that out for T, and you get 542 newtons. Well, now we actually have enough information to solve the rest of the question with just plain old regular forces. Because remember, we're going to look at only vertical and horizontal directions. We're not looking at the whole thing together. So we have T. So we have a vertical portion here. We know these two vertical ones. And the only other vertical force is V. We know T, so we know the horizontal portion of this, and the only other horizontal force is H. So when we look at our force equilibrium equations, we're just going to write a vertical force equilibrium and a horizontal force equilibrium. Okay? Our forces up have to equal the forces down. So V, I just wrote it as up because I didn't know. Negative 215 newtons is the sine, minus 135 newtons is the beam, and then this is the tension pulling up. When I solve that out, I got a negative 5.6 newtons. What that means is that that vertical force is not actually pushing up, it's pulling down, because the tension portion of that string is higher than the weight of these two. Okay, and so that negative allows me to see that that's what's happening. For the horizontal forces, it's super simple. The forces left have to equal the forces right. There's only one force left and one force right. It's H and the T cosine 41. So those two together have to equal 0. And when you solve it out, you should get 409 newtons. Okay, at this point, you should be able to work on the practice problems. Questions 1, all of them should be pretty easy except for the one with the ladder. If you skip the one with the ladder, that's fine. I will go over that with you next class. On the back, there is a question about finding the position of the center of gravity. That's an equation we did in like September. It's on your reference sheet on the left-hand column, about 6 down or something like that. Okay, so that's a plug and chug question. Don't get yourself worked up over it. It's a relatively simple question. So work on those. The answers are on Canvas, and I will go over the ladder question with you next time.